Okay, so on this one, we're still in 7.1. This is finishing up. We're getting close to finishing up 7.1. So it's determining sample size again. Suppose we want to collect sample data in order to estimate some population. So the question is, how many sample items must be obtained? So this is like what we talked about earlier. How do you know how many mice or how many people or how many whatevers you got to include in your study to get the kind of accuracy you need? More is always better, isn't it? More, if you have, if you had a new cancer treatment, new treatment for skin cancer, and you only try it on 10 people, the results are not going to be you're not going to be very confident about the results. Whereas if you do it on 100 people or 1,000 people, your confidence will rise. And we see that with statistics numerically. It'll tell us the numerical confidence. So the question is, how many need to be included in your sample to get the kind of accuracy you need? Well, here's the formula. And we come on down here. Here's the example. You plan to conduct a survey to estimate the percentage of adults who have had chickenpox. What percentage of adults have had chickenpox? I had chickenpox when I was older. People usually get it when they're younger. I had it when I was in college, actually. Find the number of people who must be surveyed if you want to be 90% confident that the sample percentage is within 2 percentage points of the true percentage for the population of all adults. Assume that nothing is known, part A, and part B, assume that about 95% have had it. And part C, does the added knowledge part B have an effect? All right, so here's the formula. Now, by the way, you might wonder right away, you might say, well, wait a minute, Mr. Heron. Didn't we do sample size before? Yeah, that's a great question. And you're going to have to distinguish one sample size formula from another on the exam. There's 3 of them. In fact, I think the best place I could go to be helpful to you would be to show you the formula sheet where they're all listed. There it is. So this is the formula sheet right on the home page of your Canvas course shell. All the formulas are here. See how there's 3 sample size right here? Boom, boom, and boom. These are all sample size. What's the difference? One's for a mean, 2 are for proportion. Proportion, and then proportion where they're known. P hat and Q hat are known. So 2 different proportion ones and then a mean one. So, okay. So we got to be a little careful there. So there they are. So which one are we doing here in part A? So in part A, it says, assume that nothing is known. Okay, nothing is known. Then that's going to be this one, right? This is known, so it's not that one. It's going to be this one, isn't it? You see that? Because this one says P hat and Q hat are known. Our part A said nothing is known, so it's got to be this one. Z alpha over 2 squared times 0.25 over E squared. So let's do that one. Over 2 squared. So I already forgot it. What is it? Z alpha over 2 squared times 0.25, 0.25 over E squared. Over E squared. So that's the N. That's sample size. Nothing known. Nothing known. And that's the same formula up here. Sorry, not there. Same formula right here. In fact, I like the way Mr. Young writes it a little bit better, but it looks different, but it's the same. Miss Lee, I mean. It's the same. Same, it'll work either way. You can use it if you're thinking, well, that's different. No, it'll come out same. See, the Z and E are both squared, and here the Z and E are squared separately. It doesn't matter. Square them together, square them separately. It's the same. All right, let's do it. So first off, what is the Z alpha over 2 thing? Well, that's that's what we've got to figure out. What are we trying to do? 90% confident. So it's for a 90% confidence interval, right? So then you go to the chart. Remember the charts? Let's go there. Go down here. I'm going to go to the charts with you and grab those. Chart. Where is it? Is it? It's this one. Yes. Okay, so I'm going to the z-charts. Lower right-hand corner, this is the z-tables. Oops, sorry. This is the z-tables. So here is our 3 z values. What do we have? We have 90%, so we want this one, 1.645. Z is 1.645. So they're in the lower right corner. 90%, okay? And then what's the E? What's the air? What did it say? Within air is E. E is air. And that means, and the way you can tell it is look for the word within. It's right here. 2 percentage points. 2%, which is decimal 0.02. So look for the word within, because that's how people speak of air, right? They say, I want to be able to estimate that within 2%. That means, give or take 2%. Air, 2%. That's air right there. Air when they say the word. When the words say within. That always signals, oh, that's the air right there. Okay, let's do it then. So what's our in value going to be? So Z alpha over our Z, so 1.645. But then we got to square that times 0.25 over the E, and the E is 0.02, and we've got to square that. Okay, so just hit the buttons on the calculator. I can show you exactly what to hit. Here we go 1.645, and then hit the x squared button, and then go times 0.25, and then divided by, and 0.02, and hit the squared button, and then hit enter. Hit those exact buttons, you'll get your answer, 1.645 squared times 2 squared equals. And I'm getting the answer, 1691.226, whatever, blah, blah, blah. Now, remember what we're always supposed to do. Does it say it on the chart? I hope it doesn't. Oh, it doesn't. You might want to add to your chart, round up, round up, round up. Sample size, you always round up. So that doesn't mean round off. Round off is where it's like 0.5 goes up, 0.4 goes down. That's rounding off. That's rounding to the nearest. We're talking round up, meaning always go up. Even 0.1 is going to go up. And Miss Lee said that right up here in the notes. She wrote round up, round up. So that's great. She did a good job telling you that. They just didn't put it on the chart. So then I round up 1692. See, even though it was only 0.2, you got to run it. Why? Because more people in your sample is always going to give you more accuracy. You can't include a part of a person, right? You can't include 1,691.2 people. So if you go down to 1,691 people, you got less accuracy than you need. You don't have the accuracy you need. So you got to do more people, 1,692 people, then you've got the accuracy you need. More is always better. So for sample size problems, in sample size, always, I would put it right in the note card. Always round up, always round up. That's the only time we do that in statistics. Only here, never again. Only on sample size.
Can you show how you did it in the calculator?
Yeah, so for the calculator, it would literally be these exact buttons. I can show it, but it literally is those exact buttons. I promise, no exaggeration. Those exact buttons. But I can do it real quick as well. So let me see here. So, all right, so here's my calculator. You can all see that right there, right in the center. Okay, let me turn this on and clear this. All right, so clear that again. Clear that. All right, so what am I going to do? I'm going to do 1.645, 1.645, and then hit the x squared. See the x squared button right over here above log? X squared times 0.25. You don't have to put the 0 in the front. It's optional. Fine, take it or leave it. Divided by 0.02, 0.02. Hit the squared button. and then hit enter. Don't forget to hit that last enter. There it is. 1691.26, blah, blah, blah. Round it up to 1692. From that. Okay, now there's a second part of this. There's part B and part C, but C will be quick. Let's do part B together. So that's part A. That's the answer to part A right there. That's all part A. Now part B says, now assume that 95% have had chickenpox. Okay, so now for part B, it's going to basically be this. It'll be quick because it's the same thing, basically. So for part B, assume that, how do they say it? 95% of adults have had chickenpox. Have had CP, chickenpox. Okay, so what does that mean? Well, that means when we go to our formulas, now we're going to use the one that says P hat and Q hat are known. See, they're changing our formulas because now we're assuming we know what the P hat and the Q hat are. They're about 90. P hat's about 95%. So it changes the game a little bit. So we use a different formula. So we're going to use N equals Z alpha over 2 squared times P hat times Q hat over E squared. That's the formula, right? Did I get that right? Yeah, Q hat over E squared. Yeah. So there we go. The Z alpha over 2 is the same as it was last time. It's because it's for a 90% confidence interval, right? So we just grab it right there, 1.645. Don't need to go to the chart again. It's the same. And the P hat, what's the P hat? Well, this is P hat. When they give us that, they're giving us P hat. We got to make it a decimal though, 0.95. And then Q hat is always 1 minus P hat. So it's 1 minus 0.95. So Q hat is 0.05, right? It's like rain and no rain. If there's a 95% chance of rain, there's a 5% chance it won't rain. And the air is the same value it was before. It's the within number. It's the 0.02. That hasn't changed. So just plug those numbers into the new formula. So now we're going to get, so I'm going to plug in 1.645 and hit the x squared button because that's squared, times, and I'll go times, and then the P hat, which is 0.95, and times the Q hat, which is 0.05, and come on down here, and then divide by the air, which is 0.02, but then you got to hit the x squared button because it's squared, and then hit enter. So literally hit those buttons, and you'll get the answer. 645 squared times P hat, Q hat, and about 2 squared. And I'm getting 321. I get the answer 321.3. Remember, we always round up. So it's better. You got to have 322 in your sample. Is this making sense here? So, and then question C finishes us off with, does the added knowledge affect the sample size? Well, our answer went from, in part A, when we didn't know anything, where we're trying to figure out what percentage of the population has had chickenpox. Back when we thought it was, when we didn't know anything, in part A, we knew nothing about what percentage might have chickenpox. We thought we would have to have 1,692 people in our sample. So what if I said to you, go out and sample 1,692 people, ask them if they've had chickenpox as a kid, versus in part B, when we assumed that the percentage of people that have had chickenpox was real close to 95%. That changed. And now to get the same kind of confidence and accuracy, now we only need to sample 322 people. Did that make a difference? Yes, for sure. It went down, way down from 1692 to 322. So by knowing something about what percentage might have had chickenpox, knowing it's around 95%, means we can survey way less people. Now we only have to ask 322 people to get the kind of accuracy that we want. And so there we go.